All right. So now this is what the scheme for second order derivative look like at a single grid point. How about the second order derivative approximation as a vector? That means if I have the second order derivative at the first grid point, my second order derivative at the second grid point, etc., up to the very last grid point, how can I write it as a matrix? What kind of matrix should that be if I want the result to be the matrix times u1, u2, etc. to un? Oh, first thing we have to really realize is that the matrix not only depends on the approximation scheme, but also depends on the boundary condition. That's actually true for all partial differential equation discretizations. You have to know what the boundary condition is to really complete the discretization. And we'll look into boundary condition a little bit later, but right now, the simplest boundary condition is essentially no boundary condition. When do we have no boundary condition? If the domain is periodic, right? I usually think of a periodic domain as a domain with no boundaries. Because what does boundary mean? Boundary means you have something special, right? And if you have periodic boundary, if you go out of one boundary, you come from the other, right? Essentially, you are saying essentially an equivalent way of thinking I have a periodic boundary condition between, let's say, 0 and 1. It's essentially saying that, oh, I'm not solving the equation on the line. I'm not solving the equation, let's say if I solve the heat equation on the steel bar. Having periodic boundary condition is saying that I'm not solving the equation on the bar that has two ends. I'm solving the equation on the ring, right? It's equivalent to saying, okay, I'm going to join this bar end to end. So 0 is the same as 1. So this is another way to think about periodic boundary condition is that there is actually no boundary. I'm solving the equation on certain geometry that actually, if I go out of one boundary, I'm actually really coming in back from the other, right? So this is the case with no boundary condition. And if I'm looking at the scheme with no boundary condition, what would the matrix be like? So for example, what is this entry here? -2. And anything else?
Then it would be 1, and then the last entry would be 1.
Okay, 1 and the last entry would be 1. Anybody want to add anything to it? Yeah, there is delta x squared, right? So everything is going to be divided by delta x squared. This is an interesting point because when we derive the approximation for first order derivative, we see our matrix, all the coefficients are divided by delta x. Now in our second order derivative matrix, all the entries are now divided by delta x squared, right? So this actually has important consequences to its eigenvalues, right? I mean, you remember when we derive the eigenvalues, when we actually solve the eigenvalues of the first order derivative matrices, everything is scaled by delta x, right? So for example, the circles are centered at -1 over delta x, and the extent of the central difference scheme is 1 over delta x times I. So here, everything is divided by delta x squared. So let's take a look later to see, okay, is the eigenvalues now scaled by delta x squared? Let's see. Okay, how about the second row?
One over delta x squared related to delta x squared.
Good.
1 over delta x squared.
It's now we see a pattern, right? So it's the same thing that happened in the first order derivative. Everything gets shifted by 1. Now as we go down a consecutive rows. So essentially, the diagonal of the matrix keeps the same as -2 over delta x squared, and the subdiagonal, the lower diagonal, keeps as 1 over delta x squared, and the super diagonal or upper diagonal keeps as 1 over delta x squared as well. And because of the periodicity, we have just a lone term over here on the lower left corner and upper right corner. That's what our matrix look like. Okay, so let's try to construct this in MATLAB and look at its eigenvalues. Okay, I have a matrix A. That is, somebody tell me what delta x, what n should I look at? I think we started with something small last time, right? Huh? 10, okay, good. So my delta x, let's say I want to solve it in a steel ring of circumference equal to 1. Okay, so delta x would be 1 divided by n. Okay, my matrix A, when I constructed the diagonal, would be -2 divided by delta x squared times identity, right? So that's what my diagonal looks like. Okay, and now if I want to add my upper and lower diagonals, I'm going to be using the same function, circ shift of in by 1 divided by delta x squared. Because the upper and lower diagonals are symmetric, so I'm just going to copy the same thing and put a -1 as the shift here. So now I have both upper and lower diagonal filled, and I have the lone non-zero entry here and here also filled, right? Okay,